Hello, everyone. This is Bruce Quimby. I'm a senior applications chemist at Agilent Technologies in Wilmington, Delaware, and I'd like to welcome you to our webinar today. In this section, I'll be speaking about US EPA method 524.2, the measurement of purgeable organic compounds in drinking water using the Agilent 8860 5977B GC MSD. For EPA 524.2, it requires the use of a purge and trap device, and so we'll be describing that system setup and evaluating it in this talk. US EPA method 524.2 is for VOCs in water, and the 524.2 method is applicable to surface water, groundwater, and drinking water using the purge and trap GCMS method. And it has four specific groups of VOCs: trihalomethanes, gases, aromatics, and the products of dehydrohalogenation. Now, I'm going to be referring to two application notes today, and I would suggest that you look at these if you're going to be using a system like this and setting it up, especially for the first time. This application note, 5991-0029EN by Jeff Hollis and Harry Prest, provides detailed summary on the advances and key parameters for successfully performing both 524.2 and EPA 8260 with, at the time, it was a 7890 purge and trap. One of the important things is it introduced BFB auto tune, which enables meeting the EPA criteria for spectral correspondence and provides improved sensitivity and stability. So this is a very good source of information to refer to, as I said, especially if you're beginning with purge and trap methodology. This application note I wanted to point out, done by myself and Anastasia Andrianova, my colleague. And in this case, this has all of the details regarding the work that I'm describing today. And the purpose of it was to demonstrate the applicability of an Agilent 8860 5977 GCMSD system, which is a cost-effective mid-range solution coupled with the Teledyne Tecmar Lumen Purge and Trap concentrator and the Aquatech LVA liquid sampler. And the ICAL range was from 0.25 to 50 microgram per liter. So the instrument configuration that we used for this work is the Aquatech liquid vial auto sampler, the Teledyne Tecmar Lumen Purge and Trap concentrator shown here, and that feeds the purged sample into the splitless inlet of our 8860 GC and goes into the 5977B MSD. Now, two key parameters that I want to point out. There's obviously a number of details that you need to be aware of when you set one of these systems up, but one of the key parameters is the use of a 6mm diameter drawout lens, which gives us better linearity and performs well in the presence of the water that is unavoidable with the purge and trap method. And the second one is the split ratio, shown here at 150 to 1. And this has been found over the years to provide the best trade-off between detection limits, long-term stability of the response and of the tune, and actually gives the best overall performance. And a lot of people would be tempted to maybe drop the split ratio to attempt to get better detection limits. I would caution you against doing that. You're certainly welcome to try it, but mass spectrometers in general don't like a lot of water going into them. Here we're looking at the tune evaluation software provided for checking that you meet the BFB auto-tune criteria. Here's the BFB, the bromofluorobenzene peak in the chromatogram shown here, where the software extracts out the spectrum shown here and then test the relative abundances against this criteria over here. And this software, this program, I should say, is available in Mass Hunter Quant environmental quant mode as a drop-down menu item. If you're not using Mass Hunter environmental quant mode, you can always obtain this program because it's available as a standalone that's installed automatically with Mass Hunter quantitative analysis. So here's our 50 microgram per liter standard, and as we can see, we've got our 80 peaks here, and the resolution is quite good with the narrow bore 20 meter 0.181 micron DB624 UI column. So this is where we start the method building. So the Mass Hunter software has a number of helpful tools, especially for when you're initially setting up a method like 524.2. And the first step, the chromatogram that we just looked at, is to analyze a standard to create a spectral library with retention times using Mass Hunter unknowns analysis. Then we will export the deconvoluted spectra from the step above over to Mass Hunter library editor and create a library of the spectra of all the peaks in our method. And then the third step is to create a quantitative analysis method in Mass Hunter Quant using the acquired scan data with the library search. We have options like we can add targeted deconvolution to the quantitative analysis if desired, and we then create calibration levels from the analyzed calibration standards. And finally, we can go on and analyze our real-world samples. So, as I said, we start out in unknowns analysis, and we bring in the sample. In this case, it's the 50 microgram per liter standard, and we analyze this against the NIST library, where all of the compounds will be searched against NIST. That is, all of the peaks will be searched against NIST for identification. And this screen here shows how we set up the deconvolution step to identify all of the compounds in our. Over here are the search results, and the next step is to go through and look at these. And what we see here is for each of these components, that is the deconvoluted spectra searched for each of these peaks, the software goes out to NIST and it will report the retention time. It'll pull the name in from NIST, report the match factor, give us the formula from NIST, and the component area. Now, the other thing that it shows us is the deconvoluted spectrum for the selected peak and the inverted NIST reference spectrum so that we can visually inspect it. And down here we have the apex spectrum, which is the spectrum of that peak before deconvolution, so we can see the degree of interferences that were near it. And here is an overlay of the extracted ions from the deconvoluted spectrum, so we can make sure that their apices all line up. The next step is to export these results over to our library editor, the MassHunter library editor. So we just select that we want all components, we want to add retention time, and we want to export it to a library. Here we're over in the library editor after exporting the deconvoluted spectra over to here, and we can edit things, change names if we want to something more widely used, and it brings over the Cas number, formula, molecular weight, and the retention time. Now, normally we don't use retention index, but if we wanted to calibrate for it, we could. So now we have a library, and the next step is to go to creating a quantitative analysis method in MassHunter Quant, and we go in and select a tab, New Method from Acquired Scan Data with Library Search. And what this will do is create a quant method for us automatically from the library spectra, and it will go in and select either 2, 3, or 4 qualifier ions and a target, all based on their relative intensity, and it'll use the most intense ion, obviously, for the target. And then, of course, we need to go in and identify some of these compounds, like 1,2-dichloropropane, which is an ISTD, and some of the compounds are surrogates, and we define those like that. And then if we want, there's a step where we can go in and set up and add target deconvolution. And this is optional, but I'll show you what the result looks like, and it's quite a useful feature. So this is what iCal review looks like in MassHunter Quant after we've set up this method. And at the top, you see the calibration table. And then in the lower left, you see the quantifier extracted ion. And here it's overlaid with the qualifiers, so we can find those, determine they're in the right ratio. Here is the target deconvolution, where this is the deconvoluted spectrum that corresponds to this peak, and this is the library reference spectrum, and we have a match score shown up here at 86.4 in this case, and finally over here we have the calibration curve. All right, so let's look at our results. This is the iCal results, and from 0.25 to 50 microgram per liter for 68 of the compounds, that's 85% of them, and we went from 0.5 to 50 for 74 of the compounds, or 93%. 79 compounds out of 80 met the EPA criteria of less than 20% RSD with a linear calibration. We did have one that required a quadratic fit with an R squared of 0.9963 for iodomethane. And the RSDs for the internal standard and surrogate compounds introduced by the Aquatech LVA were less than 5% RSD. The method detection limits were less than 0.1 microgram per liter for 73% of the compounds, that is 58 of them, and less than 0.15 microgram per liter for 83% of the compounds. So in other words, the results are very acceptable. The MDL of the gases are shown here, and they're all acceptably low. One of the benefits of the high split ratio, which may be counterintuitive, is these gases all elute when the water peak is coming out of the column, and you don't want to have too low of a split ratio or that water will cause problems with the performance of the gases. Okay, here we're looking at the analysis of a tested tap water sample from eastern Pennsylvania. We ran a number of samples from our local region here, and up in the top, we're looking at the identified compounds sorted by library match score. The column next to that is the concentration measured against the calibration curve. And then down at the bottom, these are the panels that I identified earlier for the quantifier, the qualifiers, the deconvoluted spectrum, and the cal curve for that compound. And this is one that we found interesting, this sample from one of my colleagues. And we found a number of compounds in there at fairly low levels. Here's the ISTD shown in red, the fluorobenzene. And we want to take a look at this interesting compound up here, trichloromonofluoromethane. The peak at 2.1257. So it's there at a very low level, but it's interesting. You don't often see this compound in purge and trap samples, at least I haven't. Here's the overlay of the ions from the spectrum, and as you can see, some of these are down very close to or into the noise, but that's because it's such a low level. If we look at the deconvoluted spectrum, we had a library match score of 71.8, and here's the apex spectrum where we had some interference on top of this, but the retention time matched very closely, and the spectrum's a pretty decent match for being at such a low level. And here's what the listing looks like. The delta RT from the library was 0.005 minutes. And so we're quite confident we've got trichloromonofluoromethane. Here's the results from the other samples that we ran. Here's one from southern Pennsylvania where chloroform, toluene, and the rest of these have some trihalomethane and former degreasing compounds, but most of these aren't very surprising at what was identified. Okay, so in summary, the 8860-5977B GCMSD system, equipped with a 6 mm diameter drawout lens and coupled with the Techmar Lumen Purge and Trap and the Aquatech LVA, is suitable for analyzing VOCs with an ICAL range of 0.25 to 50 microliters, 50 microgram per liter. The BFB Auto-Tune provides high sensitivity and stability while maintaining the required ion abundance ratios in the BFB spectrum. And finally, several VOCs were identified and quantified in real-world tap water samples at concentrations ranging from about 0.3 to 14 microgram per liter. In many cases, much lower than the current 524.2 MCLs. And with that, I'd like to thank you for attending our webinar today, and I'll conclude at that point.